All right, so this is problem 11-127. It's on page 491, and I'll read it to prepare. Now, automobile A travels along a straight highway at 75 kilometers per hour, increasing at 1.5 meters per second squared. Automobile B moves along a circular exit ramp of 150 meter radius with with a velocity of 40 kilometers per hour, decreasing at 0.9 meters per second squared. Okay, so here's a sketch of what's going on. Here's automobile A. Its velocity is in this direction. We're told that it's 75 kilometers per hour. And B is taking the exit and right now has a velocity of 40 kilometers per hour. The radius of curvature for the path that B is on, rho is 150 meters. At this instant in time, the angle that the position of B makes with vertical, looking at it from the bird's eye view, is 30 degrees. All right, let's see, decreasing at 0.9 meters per second squared. So that's, let's see, car B. So we know that there's an acceleration of B. I'm going to leave a little bit of space here on purpose. That is negative 0.9 meters per second squared. Now let me ask you a question. This acceleration of B, is that the total acceleration of that vehicle? This is just the tangential component, isn't it? Yeah, that's right. This is just the tangential component because what they're saying is that the speed is decreasing by this amount. They didn't say anything about the change in the direction of the velocity of car B. That's controlled by the path, and that's something we'll have to calculate. Let's see. There's one more piece of information. Automobile A is increasing speed at a rate of 1.5 meters per second. So here's the acceleration of A. And we don't have to write tangential or normal because A is not going around a curve, it's just going straight. So this is just the total acceleration of A, and that's 1.5 meters per second squared. Probably A is glad to finally be out of the traffic jam where everybody's trying to get over to get off on 6471, right? Have you guys noticed, I don't know if you've been over to Louisville in the morning, but now that 6471 is closed off, it's like everyone has given up and they don't bother trying to go that way, and going 65 south now is great. It's easy. It's no big deal. I don't know why we're bothering with the downtown bridge. I mean, Lincoln's almost basically done, right? We should have just said East End Bridge, we're done, that's it. But anyway, that's my opinion. I'm probably wrong because I haven't studied traffic patterns. And all this is going to be on the video, of course. Shouldn't have said all that. Maybe I'll edit it out. Probably not. All right. At the position shown, determine A, the velocity of A relative to B, and B, the acceleration of A relative to B. We haven't worked any problems with relative velocities or accelerations, but they're pretty straightforward. They're not difficult. I did point out the equations that you need. Let's go back and find them quickly. I do want to point them out, and then we'll jump into this problem and finish it off. The most difficult part of this problem is resolving the vectors. So we have several vectors to resolve here. Page 472 and 473 have several equations. I'll copy down the ones we really need. The velocity of B equals the velocity of A plus the velocity of B with respect to A. Now these are all vectors, so really this is two equations for the price of one, right? There's an X and a Y component here. Also, the acceleration of B is equal to the acceleration of A plus the relative acceleration of B with respect to A. Now when you look at these equations, you may be a little confused, especially when you first start off. This relative velocity here, the way you read this and the way you think about it is the velocity of B with respect to A, as if A has its own coordinate system moving along with it. And it's kind of like you're standing on A. Whatever comes after the slash, that's what you're standing on. That's your reference frame. And you're looking at the motion of the other particle from the vantage point of that particle. Does that make sense? Okay. So anyway, these are the relative velocity equations we need in order to answer some of the questions. At the position shown, determine the velocity of A relative to B. So really what they've asked for is this piece out of both of the equations. Okay? And you know what? I've got these backwards because they say the velocity of A relative to B. So in other words, they want B to be the reference. So how will I modify these equations? Well, it's pretty straightforward. If I want A with respect to B, then all I have to do is flip all the subscripts. Okay. So there we go. These are the equations we need. Yes?
Is the bottom equation acceleration?
It is, yes. Acceleration of A equals acceleration of B plus the acceleration of A with respect to B. Good question. Yes?
Is that are we solving for A or solving?
We're not solving for A or solving for B. We're solving for the relative velocity and acceleration, which is what they've asked for. So you're right. We could take these equations one step farther and rearrange them to solve for the velocity of A with respect to B. I guess I can do that here. Why don't we rearrange it? The velocity of A with respect to B would be equal to the velocity of A less the velocity of B, because all I got to do is take this to the other side. So I'm going to use a little trick here, the magic of a whiteboard. There we go. Okay, so I've rearranged that equation. Do the same thing down here. Acceleration of A with respect to B is equal to acceleration of A less acceleration of B. Basically, we just have to take the difference between two vectors. So all we need to do is find the velocity of A, velocity of B, acceleration of A, acceleration of B, add them vectorially. So basically, we have four equations to deal with here, plus a bunch of vector resolving to do. And then we'll be able to answer the question. So it's just a bunch of little pieces to plug in here. All right, let's start with the velocity of A, because that's a pretty easy one. If I wanted to write the velocity of A in vector format, how would I do that? The velocity of A is equal to, well, first of all, I need a coordinate system. Probably the most natural coordinate system is this one, x, y. So x is positive to the right, y is positive up. Okay, and so now what do I need to do? Well, to write the velocity of A, what I need to do is resolve this speed into a component. Well, it's just in the x direction, so this is 75 kilometers per hour. Now, I don't like kilometers per hour. I would rather go to meters per second, and I believe I did that somewhere here. 20, did you already do it? So it's 20 meters per second?
20.8.
20.8?
Yeah.
Okay, thanks. Now, it only has a component, or it only has magnitude in the x direction, so that's I hat. Okay, the j component of this is 0, because A, the particle essentially, A, is not moving in the y direction. Now, how about the acceleration? Well, the acceleration of A is also easy to write, because it too only has an I component. So that's 1.5 meters per second squared in the I direction plus 0 in the j direction. So we've taken care of A, right? A is easy. We've taken care of this piece and this piece. Now all we need to do is figure out the velocity and acceleration of B. Okay? So this is where it gets a little deeper. All right? So let's start off with the velocity of B and see what we've got. The velocity of B, let's see, I guess I'll pull it off here. Well, let's see, there's going to be a positive x component and a negative y component, right? The velocity of B, or the speed, is 40 kilometers per hour. Did you guys convert that as well? What did you get?
11.1.
11.1?
Yeah.
Okay, so 11.1 meters per second. Well, what do we need to do with that? Well, the 11.1 meters per second should be resolved into two components. There's going to be an x component. And how do I figure out whether I use sine or cosine?
Triangle.
Use a triangle, that's right. Just draw it down here. So here's the velocity of B. I just want to resolve it into horizontal and vertical components. Here's the I piece, here's the j piece. What's the angle back here? Do I know the angle here, or do I know the angle here? Well, you can use the fact that this line is perpendicular to this line, and this line is perpendicular to a horizontal line. Therefore, the angle between these two is the same as the angle between a horizontal line and the hypotenuse. Does that make sense? In other words, this angle is the 30-degree angle that we were given. Make sense? It's just mutually perpendicular lines. Okay. So if I want the x component, do I need to use cosine or sine? Cosine, right? Because look, the angle is touching the side that I want, okay? So cosine, I'll use my shorthand, C, 30 degrees in the I direction, plus, now I have to be a little bit careful here. I want the y component. Will it be positive or will it be negative?
Negative.
It'll be negative, right? So I actually need a negative sign, and I need sine of 30 degrees. I need a negative sign on the sine, okay? Sorry, they sound the same in English. In the j direction, and there's the velocity of b. Now, it'd be nice to go ahead and distribute these because I'll have to add them and subtract them. Looks like actually I'll have to subtract them. So let's do that. Let's see.
I have a question real quick.
Yes, please.
You said the reason it cosine is because the angle touched that.
Yes,
So
correct.
if the angle would have been the other way, it's going to be sine, right?
Correct,
Okay.
that's right. If the angle had been this way, then the angle, what I think of, is not touching that side.
Okay.
So, yeah.
Okay.
Good question. All right, we're done with our triangle, so let's get rid of it. So if you do this, let's see, I must have done this somewhere. I did it in kilometers per hour, unfortunately. So let's see, I'll need some calculator help. Please pull out your calculators. And multiply 11.1 by the cosine of 30 degrees. Let's see what we get. If I had a calculator, I'd go through it too, but I left mine in my
That's 12.7 for everything.
Got how much?
12.7 for everything, then.
How can you get 12.7?
I got 9.6.
Okay, that makes, because it has to be less than this, right? Cosine and sine are going to give you a number less than 1. Right? So 9.6 for the x component?
Yeah.
Okay, so 9.6 meters per, and thank you guys for speaking up when you have an answer. I really appreciate that. Okay, that's a good thing. And by the way, if you tell me an answer that's wrong, now is not the time when you get embarrassed. When you get embarrassed is when you get an exam score back that's very low. That's the time to be embarrassed, okay? So this is good. So how about sine of 30 times 11.1?
5.55.
5.55. By the way, you know how often you'll see your classmates after you graduate from here and go to work? Probably never. I've seen the classmates that I was with in chemical engineering not at all since I graduated. After I walked across the stage, that was the last time I ever saw any of them. Now, I've connected with some of them on Facebook, but basically this is a safe place where you can make mistakes, so please do. Okay, so 9.6 meters per second I, and 5.55 meters per second j in the negative direction. And so now we have everything we need in order to calculate the velocity of A with respect to B. So let's plug in the velocity of A. It's 20.8 meters per second. We need to subtract off the x component, so minus 9.6, and this will be in the I direction for B. Okay, that takes care of one component. And then we have to add to that the difference between the velocity of A in the j direction, which is 0, less the velocity of B in the j direction. Well, the velocity of B in the j direction is actually a negative thing. It's negative 5.5 meters per second. Both of these are meters per second. I'm dropping my units, but hopefully you get the idea. So in the j direction. Okay? So if we take 20.8 and subtract from it 9.6, let's see, that'd be 10.8 plus 0.4, so 11 point. 11 point. Wait a second. I just confused myself. Subtract 10, 10.8, have to add the 0.4 back in. Yeah, so 11.2, right? Did I do that right?
Yeah.
Okay. 11.2 I, and then this would be plus 5.55 j. Now, what does this mean? This is one of our answers, but what does it mean? Well, 11.2 in the horizontal direction, what we're saying here is if you were standing on car B and you were looking at car A, it would appear that the velocity of A is 11.2 in the I direction. Okay, so car A is pulling ahead of us on the x-axis. That makes sense. Not only is it going faster, but it has a higher component in the x direction. We only get a piece of our 40 kilometers per hour in the x direction. It also looks like that A is moving up along the y-axis. Well, that makes sense. We're actually moving down along the y-axis. And so if this is the reference, then A looks like it's moving up, at exactly opposite the speed of what we have in the y direction. So far this makes a lot of sense. Any questions? Well, we've got the second part of this to deal with, and that's this part. This is going to be a little more difficult. It's okay, I'm going to erase some of this so that we can deal with the accelerations. Okay? As I said before, the acceleration of A is straightforward, just like the velocity of A was straightforward. The difficult part will be the acceleration of B and then resolving it. So since we've finished this off, I'm just going to go ahead and erase all of the velocity stuff. We're done with that. We've got our answer, and hopefully you have it on your paper. Now, the next thing we need is the acceleration of B, and that's not extremely simple. We were given a tangential acceleration that must be resolved along the axes, right? So let's work with just the tangential component first. And then I'll calculate the normal component. Sorry. And then we'll just add the two together. Does that make sense? Because we know that the vehicle has both a tangential and a normal acceleration. Both of these accelerations need to be resolved onto the coordinate system. So the tangential acceleration is actually in the exact same direction as the velocity will be, as the tangential velocity. So this is pretty straightforward. All we have to do is take the negative 0.9 meters per second squared. By the way, notice it's actually the opposite direction of the velocity, but we're going to take care of that by leaving the negative sign in. Okay? And then what did we have to do for the velocity of B? Well, let's see, we had to take the cosine of 30 degrees I, and we had to take minus the sine of 30 degrees J, right? So that should give us the same unit vector direction, and that should work out. So let's go ahead and finish that part off. So if you guys would multiply cosine of 30 times negative 0.9 and sine of 30 times 0.9, and let me know the results, then we'll be farther along here.
Cosine's negative 0.78.
Negative 0.78 meters per second, that's in the I direction. Of course, negative times a negative will be a positive. So sine of 30 times 0.9, anybody else have that?
Negative 4.5. That's minus negative 4.5.
So it's plus,
4.5.
how is it 4.5? Because we've only got 0.9 times a number less than
0.45.
Yeah.
0.45, okay, I misheard you, I'm sorry. 0.45 meters per second squared in the J direction. Did I get it now?
I think it's negative.
No.
It can't be
No.
negative because negative times negative is
Okay.
positive. Thank you, though. Good point. Okay, so there's just the tangential component, but not only is there a acceleration in this direction, which we've represented right here, there is a normal acceleration we have to deal with as well. Now, the normal acceleration for B, if we calculate just its magnitude, not its direction, but its magnitude, it would be the tangential velocity of B squared divided by the radius of curvature. So let's figure out the magnitude of the normal acceleration, then we'll resolve it onto the coordinate system, just like we did the tangential acceleration. So the tangential velocity of B, that's the 11.1 meters per second, which will have to be squared. The radius of curvature is 150 meters. Okay, so once again, grab your calculators, please. And just tell me the magnitude of the normal acceleration. 0.822. Anyone second that?
Yep.
The units would be meters per second squared, right? Because we've got meters squared per second squared divided by meters. So we'll end up with meters per second squared. Okay, so there's the magnitude, 0.822 meters per second squared. Now we need a unit vector in the normal direction. Okay, so how will we do that? Well, once again, I recommend a triangle just to make sure that you know what you're doing. So let's see, the normal direction relative to horizontal and vertical lines. Let's see, it would have a 30-degree angle from vertical, right? Because all I've done is really copied down what I've got over here. Okay? So if I want the x component, now do I use sine or cosine? Now I have to use sine. We have to be a little careful though. Do I want positive or negative? Do I? I'm trying to resolve a vector that points in the negative x direction as a component there. So it should be negative, right? And now I can use sine of 30 degrees in the I direction. See what I'm trying to do here? I'm just representing this vector. Okay, this would be a unit vector, and I'm just resolving it onto the I and j unit vectors. Okay? Now, this side will be the cosine side, but do I need positive or negative? I need negative. Notice that this vector, again, has a negative component in the coordinate direction, in the y-coordinate direction. So I'll need minus cosine 30 degrees j. Okay? I should have left myself just a little bit more room. I don't need that anymore. We've got it built in right here. So now I need more calculator help, please. 0.822 times negative sine 30 degrees is how much?
-0.411.
Negative 0.411, thank you. And that's the I direction. How about negative cosine 30 times 0.822?
0.71.
0.71?
Yep.
Thank you. In the j direction. Okay, now let's add the two together. Let's get rid of all the mess in between, because we really are no longer interested in this one or this one, right? All we really want to do is add these components, because that would give us the total acceleration of b. Okay? So the total acceleration of b will just be the sum of these two. So 0.78 plus 0.411. Let's see. I can do that in my head, but I might get it wrong. So please plug this in your calculators as well. So that'll round up. The 4 and 3 would get, or 7 and 4 would give me another 1, and then 9 and 1. I think I got that right in the I direction. And then in the j direction, see, I just need to take 0.45 from 71, or 45 from 71. That should be straightforward. 5 is 50, 5 is 21, and 5 is 26, so 0.26j. Did I get that right? Okay. So there's the total acceleration of b. Now that was a lot of work, but the reason it was a lot of work is because we had to resolve both the tangential component of the acceleration of b and the normal component of the acceleration of b. Then we had to sum them together. Okay. So now finally we can plug everything into this equation. So we've got the acceleration of b. The acceleration of a was straightforward. I left it here on the board. It's 1.5 in the I direction, but I have to subtract the acceleration of b, which has a negative component, so that will be the same thing. Oh, here, let's write it this way. It'll be the same thing as adding. Okay. This will be in the I direction. And then I need the acceleration of a in the j direction, which is 0. And I need to subtract from that the j component of the acceleration of b. Once again, that's minus a negative 0.26. And that's in the j direction. All these are meters per second squared. Okay? All right, so finally, 1.5 plus 1.191, that's easy. That's 2.691 I. 0 minus a negative 0.26 is also easy. It's plus 0.26 j. The units of all this are meters per second squared, and that's our last answer. Hopefully that's on the video. It's pretty low. Okay, now this is the relative acceleration. What does it say? Let's interpret it. It says that if we are standing on B, if our reference is car B, it appears that car A has a positive acceleration which makes sense, right? Because car A in fact does have, we've got a negative, so it's basically those two components together, plus the fact that we've got this normal acceleration. Plus, it looks like car A is moving faster and faster in the positive y direction. So its velocity appears to be increasing to us in both the x and the y directions. Okay? Any questions? All right.